to give a survey of some primarily older papers I've written, largely under the collecting theme of sigma models on gerbes. So what in the world am I talking about? So today what I'm going to do is give this survey of work we've done over the last 15 years or so by myself and primarily with my collaborator Tony Panta, but also with various other people, concerning strings propagating on particular stacks known as gerbes. Now, we've heard a lot about gerbes in this conference, so let me take a minute to disambiguate. I think most of the time people have talked about gerbes here, they've been talking about some formal mechanism for keeping track of B fields, or how to define B fields, or other such things. That's not the sense on which I will be using gerbes in this particular talk. I have in mind something a bit different. So to explain what different thing I have in mind, let me mention an analogy. A bundle can be thought of, on the one hand, as a formal mechanism for defining a gauge field globally. You can also think of it as a manifold on which you can, well, propagate a string, for example. And it's that sense in which I'm going to be thinking about gerbes. Gerbes, like bundles, have two dual roles. On the one hand, you can think about them as places to hang B fields, so mechanisms for defining B fields. You can also think of them as examples of generalized geometry, sort of pseudo-geometric constructions that are locally, though not necessarily globally, spaces, as Urs outlined on Monday. Today's talk is going to outline work done to answer the question, to what extent can strings propagate on these particular generalized geometries? So for example, what is the quantum field theory of a sigma model on a stack or a gerbe? How in the world do you define it? What are its properties? For me as a physicist, in particular a physicist interested in string compactifications, one of the motivations was to understand, can one get new superconformal field theories, new string compactifications, from strings propagating on these generalized geometries, on stacks or gerbes? And furthermore, in supergravity theories, when should stacks enter into low energy effective nonlinear sigma models? In a four-dimensional supergravity, the four-dimensional supergravity contains a nonlinear sigma model on some moduli space of scalar fields, which typically is identified with a moduli space of Calabi-Yalls and a perturbative string compactification. But moduli spaces of Calabi-Yalls aren't really spaces. I mean, they're really stacks if you want to do it right. So to what extent in four-dimensional supergravity theories do we really have nonlinear sigma models on stacks of Calabi-Yalls? That's the sort of question that I'll be interested in addressing today. Now let me outline what I have in mind. The first part of this talk is really going to be concerned with two-dimensional nonlinear sigma models. I'm going to begin by sort of walking up to and explaining the quantum field theory of a two-dimensional sigma model with target space, a stack, or a gerbe. Now that sounds incredibly abstract, but after I sort of waltz through all the definitions and unwind a few things, what this is going to boil down to is a fancy way to talk about gauged sigma models. And the utility of this perspective is that, well, on the one hand, it will give a different way of thinking about gauged sigma models. In addition, it will also force us to consider certain exotic gauge sigma models that we had not considered previously. Those exotic gauge sigma models will correspond precisely to sigma models on gerbes as special stacks, and in particular they will have, as two-dimensional quantum field theories, some novel properties, or at least they will do something I've never seen before in a two-dimensional quantum field theory. A string on a gerbe, this special kind of two-dimensional gauge sigma model, is going to decompose as a string on a disjoint union of ordinary spaces. So that sort of decomposition is, to my mind, one of the sort of fun properties of, for me as a quantum field theorist, of these particular two-dimensional quantum field theories. And so I'm going to spend a bit of time in this talk walking through this, why it's true, and some of its applications. Then after I have put you all to sleep, telling you everything you never wanted to know about two-dimensional gauge sigma models, I'll then turn my attention to four-dimensional nonlinear sigma models. And I'll briefly outline the basic setup. This will be closely analogous to the two-dimensional case with a few technical differences. And I'll then talk about a few examples. As I mentioned before, four-dimensional nonlinear sigma models often arise in supergravity theories, where the nonlinear sigma model is mapping out something like a moduli space, or possibly a moduli stack of Calabi-Yalls. And what I'll do at the end of the talk is outline some of the structures one can see in a moduli stack of Calabi-Yalls. As a prototype, I'll primarily talk about the moduli stack of elliptic curves. I'll spend a little bit of time talking about whether it's a PSL2Z quotient or an SL2Z quotient, And then I'll go back and argue that actually if you want to build a moduli stack of two supersymmetric superconformal field theories, what you really want is neither a PSL nor an SL quotient, but actually a quotient by the meta group to give the stack a chance to correctly describe, to correctly characterize a moduli space of two-dimensional superconformal field theories. I'll talk about some implications for string dualities. Briefly, this is going to imply that in high-dimensional string dualities, the usual SL2Z action on fermions in the theories isn't quite well defined. One really wants to extend an SL2Z to the metaplectic group. And then I will conclude with some questions for the future. All right. Now, what's a stack? So first gave an outline on Monday. Let me try, but Monday was a while ago, and I don't think we've really seen any talks that have gone back and done this since. So let me spend a couple minutes reminding everyone what Urs mentioned on Monday. So briefly, there are several ways to define analogs of geometry that don't involve point set topology. One mechanism that's certainly gotten a lot of press is non-commutative geometry, where we replace point set topology by the algebra of functions on some space, and we manipulate the functions in place of manipulating points in open sets. So stacks are another generalized geometry defined in a different way. Instead of replacing a space, instead of thinking about a space in terms of points in open sets, we define a space, or we define a stack via all the maps from other spaces into the stack. We define a stack via its categories of incoming maps, in essence. Now this will include a lot of things that we already know. Examples of stacks include ordinary spaces. I can define an ordinary space by all of its maps from other spaces. That's not usually a very useful thing to do with spaces, but if you're so inclined, you certainly can. This will include orbifolds. Let me disambiguate this a little bit. In the physics community, orbifold just means a global quotient by a finite group. In the math community, the term orbifold sometimes means a much broader class of models. Since I'm a physicist, as I'm sure you all figured out by now, I will be using the physics definition of orbifold. Whenever I talk about an orbifold, I'm going to mean specifically a global quotient by a finite group, and typically a global quotient by a finite group that acts effectively. That's traditionally the sense in which the term orbifold is used in the physics community. And then gerbes are going to form other examples of stacks. So how does this work? I don't want to get into the details of this. Urs gave an outline on Monday, really explaining this as a set of lectures in and of itself. But let me try to give one quick example to give some sense of how this can work. Let me talk about orbifolds as stacks. So here I have a global quotient of some space X by some finite group G. Now if I want to define this as a stack, I said that to define it as a stack, I need to define all the maps from spaces into the stack. Well, the category of maps from some space Y into this orbifold is a pair consisting of a principal G bundle over the starting space Y, together with a G equivariant map from the total space of that bundle into X, the space you're quotienting. Now, for the physicists in the room, you might recognize this as essentially a formal way of representing the same data that we sum over in a path integral representation of orbifolds. In physics, this bundle defines the twisted sector, and the map is the map within that twisted sector. This is the stuff we actually sum over. So if I write the one-loop partition function of an orbifold as a sum over commuting pairs of group elements, that commuting pair is defining a principal G bundle up to equivalence, and then all the path integral after that is summing over these maps. Furthermore, we naturally have a category of such maps. After all, if I'm talking about bundles, I don't naturally have a set of bundles so much as a category of bundles because they have automorphisms. I can perform gauge transformations. And so these maps have automorphisms and equivalences, giving rise to an extra layer of structure beyond just sets, which is exactly as Urs outlined on Monday. Now, what can I do with this? Well, how do I build the quantum field theory for a nonlinear signal model whose target is a stack? In general terms, it seems like a natural thing to do. The path integral of quantum field theory involves a sum sum over maps into something, a stack is defined by its incoming maps. So this seems like a natural setup, but when we get into the weeds of the details, it gets a little more fuzzy. Here's one approach. Stacks can be locally presented as spaces. I can think about them, I can basically put what amounts to open sets on them and try to cover a stack. So couldn't we just imagine gluing a bunch of nonlinear signal models on those open sets? Unfortunately, it's not really known how to do this to define an entire quantum field theory. So bits of this are known. Witten back in 2005 as part of his work on the Durham complex, proposed something like this for the perturbative part of a nonlinear signal model. He set up a description of the perturbation theory of a nonlinear signal model in terms of data defined locally on the target space. But neither Witten nor anyone else has ever figured out how to glue all the non-perturbative physics in that setup. So this is, it's a start, but we can't actually build the full quantum field theory this way. So here's another attack at this. Stacks can be presented as group weight quotients. We imagine taking some big space, and then we just stick together points in some pseudo fashion. So couldn't we just implement those group weight relations in a signal model in a space? Well, the problem with that is I don't really know how to do that. The only way I know how to stick together different points is via gauging a group action. To gauge a group OID action would, the last time I checked, seem to require some sort of generalization of what we currently mean by gauging and gauge fixing. So without having any insight into some sort of extension of quantum field theory, this doesn't really seem to be a good approach either. Another question you might ask at this point, is this even possible? Why do I know I can even do this? Maybe I can't. Maybe nonlinear signal models can only be defined on spaces, or maybe spaces plus orbitals. I mean, that would certainly be consistent with what a lot of people used to think. What reason do we have to believe that such a quantum field theory can even exist? Well, to give a bit of background, since before this work began, the Gromov-Witten community had been working on, and nowadays actually possesses, a notion of Gromov-Witten invariance for stacks. Now that's neither necessary nor sufficient for defining a quantum field theory, but it's suggestive that maybe this program has an endpoint. So, how can you hope to define the quantum field theory of a nonlinear signal model whose target space is a stack? So here's the trick, and here's how this relates to gauge signal models. Every or nearly every smooth Lie-Mumford stack can be presented as a global quotient of a space in a group where the group need not be finite and need not act effectively. So these are not going to be orbifolds in the physics sense. I'm going to be gauging, for example, continuous rather than just finite groups. And then the game is, to any such presentation, you can associate a gauge signal model. Now, that's not the whole story in and of itself. Different presentations of the same stack can yield very different quantum field theories. I can give you examples in which one presentation is manifestly a conformal field theory and the other presentation is manifestly not a conformal field theory. So the way to really do this right is to associate stacks to universality classes of renormalization group flow of such gauge signal models. And in fact, there's a longer story. If you'll forgive me an aside, I think I've got time to say something quickly. There's a sort of general yoga here about how these things sometimes work. So here what I've told you is that given a presentation of a stack as a global quotient by some group, I can associate a gauge signal model, and then equivalences of presentations. Two presentations that define the same stack should be related by the renormalization group. There's a similar game people play in derived categories. Given a complex of sheaves, one associates a set of branes and anti-branes and tachyons, and then quasi-isomorphisms between complexes get realized physically via renormalization group flow. And analogous structures seem to help elsewhere, though I'm not going to take the time to walk through those in any detail. The point is just that there's some yoga here in which renormalization group flow seems to give some physical realization of homotopies and categorical equivalences to be rather vague. All right. So let's go back to the stacks. So I told you that essentially every smooth Lie-Mumford stack can be presented as a global quotient by some group, so we can just associate a gauge signal model to that and let renormalization group flow wash out any differences. Now, in this language, what's a gerbe? Well, a single model on a gerbe can be described in several equivalent ways in these two-dimensional theories. So one way is as a gauge theory in which a subgroup of G acts trivially. This is maybe the description that makes the most sense coming from a stack perspective. If I want to think about a gerbe as a special kind of a stack, then in this language of quotients, what distinguishes a gerbe is the fact that some subgroup of the group you're quotienting acts trivially everywhere. So in the special case of an orbifold, if I'm orbifolding a space X by some finite group, and that orbifold is a gerbe, what that means is that there's some subgroup of the group that acts trivially everywhere. So for the physicists in the audience, in effect, every single point on the quotient is a singular point. We're used to orbifolds that have maybe points or curves that are fixed under the gauge group. Here we have the entire space fixed under the action of the orbifold group, which is something that people hadn't really seriously thought about in the past. Now, it turns out that there are some other ways to think about this that are equivalent in two dimensions. Another way, which I'll focus primarily in this talk today on this first perspective, but also spend a little bit of time talking about these things as gauge theories with restrictions on non-perturbative sectors. It's not immediately obvious from anything I've said or from general statements about stacks, but it turns out that these two-dimensional gauge theories in which some subgroup of the gauge group acts trivially can also be understood as gauge theories by the sort of effectively acting coset in which you restrict the allowed non-perturbative sectors, which gives a clue as to some of the complications we're going to run into in making sense of the quantum field theory of these things. There's another way to describe this in terms of gauge theories, a couple of TFTs, but I'm not going to touch on this last way at all. I mentioned it just for completeness. All right, so I told you a signal model in a gerbe is basically going to correspond in physics to a gauge theory in which a subgroup of the gauge group acts trivially. Now, if you're a physicist, that should bring to mind some potential issues, which are part of the reason why people hadn't considered this previously. Mathematics and stacks remembers even. That's one of the nice things about a stack. I can quotient a point by a group, and the result as a stack will be different from a point. As a space, if I quotient a space by a group, who cares? Nothing happens. It's identical to a space again. But stacks actually remember even trivial group actions, and that's why gerbes are non-trivial as kinds of stacks. But in physics, why should the analogous statement be true? Why is such a gauge theory any different at all from a gauge theory in which one has gauged an effectively acting coset? So to try to make this a little bit more precise, let's suppose I have a U1 gauge theory and declare that all the electrons have charge 2 instead of charge 1. What possible difference could that make? Let's suppose here, somewhere a couple hundred years ago, some physicists had declared that all the electrons had charge 2 in standard units rather than charge 1, and the charges of all other fields were also multiplied by 2. I mean, that's basically what I'm describing. I'm claiming that makes a difference physically, but how can that be? On the face of it, that's just a notation. That's just a convention. That doesn't seem like it can have any physical meaning. It turns out it can have physics, but the answer is subtle and entirely non-perturbative. So if my two-dimensional worldsheet is compact, then one way to think about this is as follows. To specify a matter field that has some charge in a U1 gauge theory, the good way to specify it is in terms of what bundle it couples to. If the gauge field is associated with some line model L, then the good way, the invariant way to say that a field has charge Q is to say that it's a section of the Qth tensor power of L. Now, if I start playing games like replacing all the Q's with twice Q, that means I've changed the bundles, which means the fields have different zero modes, which changes all the anomalies, which means the physics is different. So perturbatively, nothing has happened, but non-perturbatively, depending upon how I've defined the theory non-perturbatively, there can be a difference. There doesn't have to be a difference. It all is buried in how the theory is defined non-perturbatively. On a non-compact worldsheet, if my worldsheet is just a complex plane, this argument breaks down because all line bundles are trivial. But there's something else I can do. So here I can distinguish a gerbe case from a non-gerbe case by adding massive charged fields of charge plus or minus 1. Now, that seems like Here, if I've added some massive field of minimal charge, that's certainly going to distinguish that theory from the theory I had before. But then I can also take the renormalization group scale and lower it and integrate out those fields, which would seem to obliviate that distinction. On the other hand, I can also sense their presence or sense their existence by using the two-dimensional theta angle. The 2D theta angle basically acts like an electric field. So the game I can play is I can build a capacitor and then make it big, or try rotating up the theta angle. And as I do, it will start pair-producing matter. So with a big enough field, I can pair-produce any massive states. In particular, I can pair-produce these charged ±1 states, even if their masses are above the RG scale. And thereby, and furthermore, the things that can pair-produce will determine the theta angle periodicity. So I can distinguish these by these theta angle arguments, and also use defects if I'm so inclined. So let me give you a quick example of how these differences arise. Let me compare the ordinary two-dimensional supersymmetric CPN model, CPN-1 model. This is a U1 gauge theory with n fields of charge 1, to a gerbes version, a U1 gauge theory with n fields of charge k. If we walk through the details, we run into some differences. The anomalies are different. In the ordinary CPN model, there's an axial U1 that's anomalous and broken into a finite group. Here, the gerbes version is broken into a different finite group. The correlation functions are a little bit different. The quantum cohomology rings turn out to be different. These two theories have different physics. Furthermore, this is going a bit slower than I thought it would, so I don't really have the time to walk through this carefully. If you think carefully about what these correlation functions are doing and how these are related, you can convince yourself pretty quickly that there must be, that the gerbes theory looks a lot like the original theory with a restriction on the non-perturbative sectors. Now, with that in mind, there's another technical issue. So far I've established that physics can actually see gerbe structures. Physics can actually see the same sort of structure that arises in a stack. So that's good. But now we have a problem. If these theories are equivalent to restricting the allowed non-perturbative sectors, well, that violates one of the axioms of quantum field theory, something called cluster decomposition. Similarly, if you compute massless states, you find that these theories have multiple dimension zero operators, which again signals a violation of this particular axiom of quantum field theory. But there's a fix for this. The fix is that these particular weird gauge theories, these strings on gerbes, turn out to be physically equivalent to strings on disjoint unions of spaces. These things also violate cluster decomposition, but in a manner we understand and control. For example, these theories are still unitary as quantum field theories. So there's still some perfectly well-defined good quantum field theory in there I can manipulate, and the fact that we have a violation of cluster decomposition is just some artifact of the fact that I'm describing a string propagating on a disjoint union. So let me see if I can outline a couple variations of this. For a nonlinear sigma model on a banded gerbe, the result looks something like this. The quantum field theory corresponding to the gerbe. This gauge sigma model with a trivially acting subgroup is the same as a quantum field theory of a disjoint union of copies of the underlying honest space with variable B field determined in a sort of simple fashion from the characteristic class, the gerbe and the particular component on which you're sitting, where the components are indexed by irreducible representations of the group in question. There are other variations elsewhere. For example, for non-abelian two-dimensional gauge theories, if the matter of the field happens to be invariant under a subgroup of the center of the gauge group, the same setup I'm describing here, then the gauge theory will decompose with factors differing by discrete theta angles. So schematically, a pure SU2 gauge theory in 2 dimensions is the same as a disjoint union of a pair of pure SO3 gauge theories in 2 dimensions with different discrete theta angles, which can be checked in various ways, but I could give a whole talk just on that, and there's just no time. Here's a schematic idea of how this actually makes sense, why this works. So a path integral with a restriction on non-perturbative sectors, I can think of as being something like this. I can insert a projection operator, which basically sums over B fields, or sums over certain B fields. And then these different phases, summing over them, has the effect of annihilating any contribution to the path integral that doesn't have the right degree. So it annihilates any contribution from a non-perturbative sector of the wrong degree. But schematically, I can take the sum and pull it outside the path integral, and so this looks like the same as a sum over elements of this union of path integrals with variable b fields. So schematically, this is how this decomposition business actually works. I think I've got enough time to walk through an example. I apologize for the mathematicians in the audience. I find concrete examples to be very helpful, and being a physicist, I find a physics example as being very helpful. So for the physicists here, hopefully this will be illuminating, and for everyone else, I apologize. You can wake up again in a couple of minutes once I get past this. So let me consider the following example. Z2 gerb over an orbifold by Z2 cross Z2. So specifically, let's consider a D4 gauge theory, where D4 is the 8-element dihedral group. That's a Z2 extension, a Z2 central extension of Z2 cross Z2. Decomposition predicts that if this Z2 acts trivially, then this D4 orbifold should decompose as a disjoint union of two Z2 cross Z2 orbifolds, where one has something called discrete torsion, some discrete analog of a B field, the other doesn't. Now, we can see that explicitly when we compute partition functions. If we enumerate the elements of D4, well, the partition function of this D4 gauge theory, of this D4 orbifold on a 2 torus, looks like a sum over commuting pairs of elements inside D4, weighted by 1 over the order of D4. Now, because that D2 center acts trivially, each D2 twisted sector, each one of these ZGHs, will be the same as some Z2 cross Z2 twisted sector, appearing with some multiplicity according to the number of times, since I can multiply these things by elements of the center, except for the fact that these particular twisted sectors of the Z2 cross Z2 orbifold are missing. They're missing because although these pairs commute inside Z2 cross Z2, they don't commute inside D4. So as a result, when I compute the partition function of that D4 orbifold, what I get of the factors looks like the partition function of the Z2 cross Z2 orbifold minus some of the twisted sectors. So harking back to the idea that these are orbifolds in which or these are theories in which you restrict to the non-perturbative sectors. Furthermore, when you count these factors, you find there's an overall factor of 2. And furthermore, the twisted sectors that are omitted have the entertaining property that when you turn on discrete torsion, the contributions from these sectors get a sign. So omitting these things is the same thing as taking a partition function which has them, and adding to that a partition function in which these are each multiplied by a sign. They cancel out of the sum, and so the result looks like this. And in particular, the partition function of this D4 orbifold is the partition function of that particular disjoint union, consistent with the predictions of decomposition. All right, now I've told you everything you never wanted to know about decomposition. Let me tell you a couple of the fun applications. I mentioned at the beginning that the Gromov-Witten community has some notion of Gromov-Witten theory for stacks. Implicit in here is a prediction for those Gromov-Witten invariants. The Gromov-Witten invariance of stacks corresponding to gerbes should be the same as the Gromov-Witten invariance of disjoint unionless spaces. And this has since been proven in work of various Gromov-Witten theorists. Yes?
But mathematically, you don't see this at all, that somehow your gerb is equivalent to a disjoint union of spaces.
Oh, there are lots of ways to see it mathematically. There are other ways to see this mathematically. I focused just on the physics, but maybe since there are lots of mathematicians here, I should have added some mathematics slides as well. If you look at the K theory of one of these gerbes, the K theory naturally decomposes. If you look at the possible sheaves on a gerb, the sheaves decompose. The reason for those decompositions is that although the gauge theory acts trivially on the base space, or although some subgroup of the gauge group acts trivially on the base space, it doesn't have to act trivially on any bundle you put over it. And when you walk through the implications of that, for example, for K theory, you get that K theory decomposes. You get some decomposition of sheaves on these spaces that follows the exact same pattern. So, yeah, since there are many mathematicians here, I should have emphasized this a little bit more. But there are also, this physics statement also mirrors mathematics results for various properties of gadgets on gerbes as well. It puts them all together. So there's a prediction for Gromov-Witten theory. This was something new. They had some fun proving. There's also some fun games one can play with gauge linear signal models. I may actually be the only person in the room with any experience with gauge linear signal models, so maybe emphasizing this is not the most useful thing to do. But there is some fun story in which you take one of these gadgets called gauge linear signal models, which will describe spaces. You add you play games with multiplying all the charges of all the fields to make them minimal. Add some massive minimally charged stuff. You can produce things that look like branch double covers, where away from the branch locus, the minimally charged stuff is all massive, but becomes massless along the branch locus. This gives us a way of understanding some of the Wiener-Ginzburg points in some GLSMs that previously been rather confusing, intersections of quadrics. This also gives rise to a physical realization of something called Kuznetsov's homological projective duality. But that's neither here nor there. Let me pose a question to the audience. Is there a three-dimensional analog of this? This fun bit of physics, this decomposition, is specific to two-dimensional gauge theories. In 3 dimensions, I don't expect the entire theory to decompose, but there may be some sort of analogous decomposition of some of the defects in the theory. I don't have a good answer to this question, but this does seem like an appropriate question to pose to the audience. All right. Well, now that I've put everyone to sleep telling you about two-dimensional quantum field theories, let me now put you all to sleep talking about four-dimensional nonlinear signal models. What I want to do next is briefly outline some of the differences one encounters when talking about four-dimensional, low-energy effective signal models whose targets are stacks, as arise, for example, where it's potentially arise in four-dimensional supergravity theories. And then, since the typical targets are going to be things like moduli spaces and flageols, which can be somewhat complicated, as a prototype for what can happen, let me talk about moduli stacks of elliptic curves and some of the ways gerbe structures appear there. And I'll close with some implications for string dualities and some questions for the future. Now, in 4 dimensions, one can play almost the same game. One has the same sorts of questions. So in a 4-dimensional nonlinear signal model, I can interpret a 4-dimensional nonlinear signal model on a gerbe as a gauge signal model. Or conversely, I can interpret a gauge signal model as being a nonlinear signal model on a gerbe, on a stack. In the case of gerbes, there's again an issue that it's not clear why physics will necessarily want to keep track of trivial group actions. Some of the arguments from 2 dimensions work, some don't. So on a compact 4-dimensional space-time, to correctly, unambiguously specify the matter fields, I need to specify line bundles, and as before, one can argue that that means that the physics will keep track of even trivial group actions. For non-compact 4-dimensional spaces, I can no longer appeal to 2-dimensional theta angles, since I'm no longer in 2 dimensions. What I can do is play games with charged black holes and argue that they can effectively detect the presence of minimally charged matter. I can also play games with adding defects to the theory. Now, so schematically, 4-dimensional low-energy effective nonlinear signal models will work in a fashion that's rather analogous. Let me now turn to some examples of stacks one might actually care about in a 4-dimensional low-energy effective nonlinear signal model, or at least prototypes for moduli stacks of flageols. Let me talk a little bit about moduli stacks of elliptic curves as a prototype for the sorts of things that can happen for moduli stacks of flageols. Now, as probably most people here know, at least at first order, a moduli stack of elliptic curves looks like a quotient of the upper half plane by PSL2Z. Given a point on the upper half plane, PSL2Z, well, SL2Z acts in this form, where A, B, C, and D are elements of SL2Z. However, in this expression, the center of SL2Z acts trivially on the towels. So if I just care about parameterizing towels, then I might as well just quotient by SL2Z modulo the center. Now, there's more to the story. First, let's think about the line bundle of holomorphic top forms. I claim claim that the line bundle of holomorphic top forms is not well defined over the PSL2Z quotient. And let me add, this is some well-known result of the algebraic geometry community. Let me review this en route to telling you something that's a bit more novel. So let's see this. Let me let Z be some affine coordinate on that complex plane covenant. Then under the action of SL2Z, if the complex parameter for the torus, tau, maps to A tau plus B over C tau plus D, then it's a standard result that Z will map to Z over C tau plus D. So the holomorphic top form, trivial one form, dz maps to dz over C tau plus D. Now the center of SL2Z acted trivially on tau, but it maps Z to minus Z, and it's dz to minus dz. So if I want to build something like a line bundle of holomorphic top forms, that's not going to be well defined over a PSL2Z quotient. The fix for that is standard. We define the moduli stack to be the quotient of the upper half plane by SL2Z rather than PSL2Z. That line bundle of holomorphic top forms, the Hodge line bundle, is naturally defined over this SL2Z quotient, but not really naturally defined over that PSL2Z quotient. And in physics, that holomorphic top form corresponds to something, a particular operator in the conformal field theory, something called a spectral flow operator. So if I want to build something like a moduli space of superconformal field theories, then in order to get a well-defined line bundle of these operators, I definitely want at least an SL2Z quotient. Now, the trouble is, if I really want a moduli space of superconformal field theories contain other things than just spectral flow operators, and it turns out I need a bit more. In particular, the Cairo-Ramon vacuum of the two-dimension of a sigma model on a elliptic curve, these are not well defined under either PSL or SL. So under SL2Z, here I've got a triple consisting of the complex structure parameter, the torus, an affine parameter, and then the Fock vacuum. Tau maps to A tau plus B over C tau plus D as usual. The coordinate on the torus, Z, maps to Z over C tau plus D, as mentioned a minute ago. And it turns out that the Fock vacuum maps to plus or minus the Fock vacuum divided by a square root of C tau plus D. There's essentially a square root branch net ambiguity that pops up. So a sign ambiguity in the action of SL2Z on that Fock vacuum. So SL2Z, therefore, is not well defined. So if I want to build something like a line bundle of Fock vacuum, then I can't quotient by either a PSL or an SL. Instead, I need a quotient by some sort of Z mod 2 extension of SL2Z. And the result is that a line bundle of Fock vacua is well defined in families on a quotient of the upper half plane by the metaplectic group, MP2Z. Well, this is the unique non-trivial central Z2 extension of SL2Z. And we conjecture, in fact, the moduli space of, well, complex structures of superconformal field theories for elliptic curves is this quotient by the metaplectic group rather than just SL2Z. So if I wanted to build something like a universal superconformal field theory for elliptic curves, I'd need a quotient of the upper half plane by the metaplectic group rather than SL2Z or certainly PSL2Z. Now, I'm beginning to run short on time, so I briefly run through a few other things. This appears to have some implications for string dualities, or at least there are some analogous sign ambiguities in three-dimensional string dualities. And it looks like in many such cases, other SL2Zs should be replaced by copies of the metaplectic group, where the point is that the extra Z2 of the metaplectic group is acting on fermions of the theory. So in other words, I'm going to claim that in order to define the action of high-dimensional string dualities on theories, including their fermions, not just their bosonic parts, we actually want a slight extension of SL2Zs. For example, in T-duality of a 2 torus for, well, briefly, roughly the same reasons as before, we replace it looks like we need to replace the SL2Z factors in SO2,2Z by copies of the metaplectic group, where the extension is keeping track of how the T-duality acts on the fermions. For, oh wait, sorry, wrong direction. For a 10-dimensional type 2B S-duality, there's an analogous and independent story. If you look at how 10D S-duality acts on the fermions of type 2b, there's again a sign ambiguity which is naturally fixed if you replace SL2Z by the metaplectic group, where that extra Z2 is just acting on the fermions of the 10-dimensional theory. For all the bosonic parts, you take MP2, project it to SL2, and proceed as before. And this was independently noticed by Dave Morrison. For M theory on a torus, here we look at the action of the mapping class group on fermions. And here there's an analogous sign ambiguity. So the issue here is that, in effect, to define how the mapping class group acts on fermions, then we take the usual mapping class group action on the bosons and we look at how it acts on, we take a spin length of it in essence. And thinking through the sign ambiguity that involves gives, again, an action of the metaplectic group, where again, the extra Z2 is just dealing with the fermions of the theory. And then similarly for U-duality in 9 dimensions, it looks like that's an MP2 instead of an SL2. And analogously in low dimensions, we have a paper where we just walk through this down to, I think, 7 dimensions, computing Z2 extensions of essentially U-duality groups, and checking that these things are all secretly consistent with one another. For example, the T-duality of T2, the S-duality of 10-dimensional type 2b, the mapping class group of M theory, and this 9-dimensional U-duality group, these are all in principle intimately related. Changing one should imply that the others change as well, and each of these can be derived independently from the other, providing a nice self-consistency check of this. All right, I think I have just a minute over time, so if the organizer will give me just a minute or two more to finish up. You can ask about what moduli stack is sensed by defects in 10-dimensional type 2b, PSL, SL, or MP2. In F-theory compactifications, there's already a known defect which senses the center of SL2, corresponding to a particular cadirofiber of elliptic vibrations. So definitely the SL2, at least the SL2 quotient is relevant, and one suspects the metaplectic group quotient, but it is an open problem to find the D7 brain configuration that senses the Z mod 2 specific to the metaplectic group. That has not yet been done. And I'm basically out of time. If you're curious, I can tell you about higher dimensional examples. Examples of moduli space apply the threefolds, for which we know the global structure of the moduli space to the extent of being able to compute the Picard group and where the Hodge line bundles lie inside there. And in these examples, we can also, I can also tell you where to find this line bundle of Bach factor as well. All right, so far I've told you about quantum field theories in two-dimensional sigma model, or the quantum field theory for two-dimensional sigma models whose target spaces are stacks. And again, this is a fancy way to talk about gauged sigma models in 2 dimensions. I've talked about a specific set of fun properties that arise when you think about gauged sigma models from the perspective of stacks. When you try to understand how physics can encode even trivial group actions, then you eventually come into the idea that a string on a gerbe should be the same as a string on a disjoint union. I've briefly outlined 4-dimensional sigma models, some moduli stacks that are pertinent for 4-dimensional sigma models, some implications for string dualities, and briefly some questions. One could ask about the relevance of gerbe structures on moduli spaces to 6-dimensional 2-0 theories. I've already previously asked, is there a D7 brain configuration that says the Z2 specific to the metaplectic group in 10-dimensional type 2b strings? Is there some sort of 3-dimensional analog of decomposition? There's a conjecture here about non-triviality of Hodge line bundles, but that would take a while to explain. And given that I'm a few minutes over, let me stop here.
Questions? Yep. I have a question to a point you said at the very beginning. When you replace your target stack by an equivalent stack, then you say on the quantum field theory side, you see that as a renormalization group flow. So is renormalization group flow, do you have some rigorous perspective on that?
Absolutely not.
Describe it as,
Absolutely not. So when I say that, and for all other occurrences of renormalization group flow, for example, in derived categories, and now quasi-isomorphism gets represented as renormalization group flow. What's going on is that we can check we have lots of concrete examples in which this happens. We conjecture that this is always happening. We have no reason to believe that there are any counterexamples, but no, we do not have anything like a rigorous proof. And it's not out of the question. Someone might write a paper, I don't know, maybe someone will write a paper next week, say, finding a counterexample. I think it's very unlikely for reasons I can discuss in greater detail later. I think for various physics reasons, you know, I'm making a big deal about certain equivalences that in the physics community actually look more nearly routine. So if someone could find a counterexample, it would be of great surprise to, I think, to a quantum field theorist looking at these examples. But I absolutely cannot give you a rigorous proof that the renormalization group will always match those categorical equivalences. It naturally meshes with how quantum field theorists' intuition for these things. It works in all of the concrete examples we've checked, and people have tried to take some very different looking presentations and just do basic consistency checks. They really do flow to the same point. So I would be absolutely stunned if anyone could find a counterexample, but no. We do not have a rigorous proof, so I cannot rigorously exclude the existence of a counterexample.
but it would give a very nice new perspective for renormalization.
Oh, sure. It would also mean that, it would give a wonderful new perspective on renormalization. It would teach us a great deal about quantum field theory. It would be extremely interesting for that reason. It would also be a tremendous frustration to people who spent chunks of their careers working on, for example, derived categories in physics, because it would mean that many of these statements that we've all assumed that are true were actually wrong. So it would be of great interest if it could be done. It would be very illuminating. I don't think it's very likely, but if someone can figure it out, hey, it would be fun to see. I cannot dispute that.
To insist a little bit in the spirit of Alex's question, people have been looking at renormalization group flows for two-dimensional CFTs and how they relate them.
Sure.
Okay? Take minimal models. That is the very early days. Can you say in which sense these models are concretely related by homotopes?
Oh, I have absolutely no insight into minimal models at all. So part of what's going on here is that we have supersymmetric gauge theories in which or supersymmetric theories, just throwing derived categories into the mix, which also have a clear connection to geometry. So for something like a minimal model, I have absolutely no insight, and these theories give no insight into the RG behavior of minimal models. So certainly there are supersymmetric minimal models, but I do not know, okay, I could talk about Gerbes models and Calabi-Yow's, but if I just take a random minimal model, I have no simple connection to geometry in a way such that geometry naturally captures any features of the minimal model. So in these models, for example, things like chiral rings will be naturally computed by some cohomology theory of something, depending upon whether or not stacks or derived categories or what have you. And so that also implies a number of consistency checks. If you had different presentations that didn't flow to the same point, then that would mean you had two different theories with the same chiral ring that end up somewhere different, which is, conceivable but more confusing. For a minimal model, I don't have any simple there's no simple geometry I can compare to. And we can go into a longer discussion of taking a minimal model and maybe computing a chiral ring to some sort of Lee-Algebra cohomology computation, but I don't know how to relate those sorts of computations to anything here, if you see what I'm driving at. So, so I have no insight into minimal models, and I don't think this will give any insight into minimal models either.
So what should be the homotopy in varying quantities that are the same?
So in a minimal model,
that are related by some homotopy.
So in these theories, so for minimal models, again, I have no insights. In here, things like chiral rings, depending, so our discussion is covering a number of things. We were talking about derived categories. The answer is going to include things like massless states on open strings. So topological field theory states, broadly speaking. So in a closed string theory, it would be chiral rings. Well, I guess the X groups also correspond to chiral rings in the open string as well. So broadly speaking, chiral rings, data captured by a topological field theory or some sort of holomorphic field theory, that's the sort of data that in principle should be RG invariant or or suitably well behaved under RG flow, that we can use it to sort of give some consistency checks that things ought to flow to the same point. Whereas for something like minimal models, okay, you don't need to define these things, I can't relate it to this, so I can't make any predictions.
Any other questions?
Maybe related to this question, actually minimal model can be seen as course set models, but just have to know the
Yes, absolutely.
Like
So for
in
example,
in your
sorry, I interrupted. I interrupted and I did so in such a way that I couldn't actually hear the rest of your actual question. Could you repeat the question this time with me being careful to shut up while you
No, I just said that minimal model are actually concept models just at the low levels or in the deep quantum phase. Like, so it looks like it could fit in your picture in some sense.
Yeah, that's fair. So the difference is that here, so when I'm thinking about gauge signal models, I didn't say it, but really I'm thinking about weakly coupled gauge signal models. So in a Kazama-Suzuki coset, you're right, I can take a gauge WDW model, depending on the gauge WDW model, that's often going to be some sort of minimal model. Here what I have in the back of my mind are theories with a weak coupling relationship to geometry. So if I take a Z2 orbifold of a torus, for one example, I can take an orbifold and do perturbation theory and the curvatures of the atlas. So for a toroidal orbifold, that means I can effectively work a free field theory, which is certainly how people think about toroidal orbifolds. And for more general things, if I have like an orbifold with some other compact clavier, then if I'm go to a large radius limit with the clavier, again I have a weak coupling limit at the atlas, and I can do perturbation theory in the gauge signal model about that weak coupling limit and expect that the things I compute will have some sort of geometric relationship to that clavier atlas, or in this case some gauging of that clavier atlas. For something like a WW coset, where the coupling constant is the level, okay, I could make the level really, really big. I could try to take the level to infinity, but then I don't. It may be possible to apply these sorts of ideas to make statements about gauge WZW cosets for near infinite levels, but I don't really know what that would mean. The usual story behind WZW models and Kazama-Suzuki cosets is that because the level is quantized and small, so the coupling constant is big, the things you compute in the theory don't have any simple relationship to either the geometry of the group manifold in the case of the WW model or the geometry of the coset in the case of the Kazama-Suzuki coset. Basically because you're working in what amounts to a strongly coupled theory. So, we could work around that by taking the level of infinity, and then, if it doesn't work out, one could probably make some statement, but I don't have anything simple to tell you.
Can I ask you a question? Do we have time? I was wondering, maybe the statement about the disjoint sum spaces sounds a bit surprising. Do I understand correctly? Is it really about sum over instant on segments, right?
It's weirder than that. So in the case of the orbifold, what's happening is that you can use in the case of an orbifold, let's suppose that there's a trivial Z2, so I've got a Z2 gerbe. And that means the orbifold has a pair of dimension 0 operators. So that is the usual identity, and then some other operator that I'll call I, because I'm not being very creative at the moment, which is the other dimension 0 operator, but in the twisted sector of the Z2 orbifold. The game you play is to build projection operators that are basically 1/2 of 1 plus or minus I. And these projection operators end up projecting the states onto, basically 2 different copies of something. So the reason for the good reason for that decomposition in the case of an orbifold is that you can actually build projection operators, which will completely disentangle the states from one another. So it's tied into the fact that you have multiple dimension zero operators, where one is what you would usually call the identity, and the other dimension zero operators are lying in twisted sectors. So you can use them to construct projection operators that will project you onto different factors. And the relation, I also mentioned that this is equivalent to restriction on non-perturbative sectors. This is, maybe I answered the wrong question actually. This is, so there's also, these things are, in two-dimensional theories, these are also equivalent to theories with restrictions on non-perturbative sectors. That doesn't work in higher dimensions. For example, in I'm running quite a bit over time. Tell you what, I can go on for a while. I think I'm already well over. So the people's lunch won't be delayed too much. Why don't we discuss this afterwards so that the next speaker can talk and then everyone can get to lunch somewhat on time. How about that?
Yes, so thank you very much again.